So in this video, we're going to introduce our inverse trig functions. Let's start by looking at this parabola quadratic function that we have right here on the left-hand side. We learned a long time ago that we had the vertical line test, the vertical line test, which said if I drew a vertical line through this function or through this graph and it only touched my graph one time, then we considered this a function. So we could draw a straight line here. You can see that in my vertical line is only touching the graph one time, and therefore this would be a function. Then we got a little bit more specific and we said, well, not only do I want to know if something is a function, but I want to know if it's a one-to-one function. So we have another line test, which was the horizontal line test. It said if my line again touches my function in more than one place, then it's not a one-to-one function. And you can see here that my quadratic or the parabola is not one-to-one because it's touching in multiple places along my graph. What if, however, I look over here at this cubic function? Just to be on the safe side, if I were to draw a vertical line, you could see that it is a function. And then you can also see by the horizontal line test that it is a one-to-one function because each of these pink horizontal lines only touch the graph once. Now, what is the big deal about a function versus a one-to-one function? One-to-one functions are special because if a function is one-to-one, then we know it has an inverse. So a function has to be one-to-one in order for it to have an inverse. And in math, a lot of times, we can kind of manipulate or restrict, it would be restrict, what we're doing so we can force a function to be one-to-one. So here I have just a portion of that quadratic graph. Notice that it passes the vertical line test, so it is a function. And by restricting this to where I am only looking at half of the graph in this particular case, I can use the horizontal line test to show that it is also a one-to-one function. So by only looking at a particular portion of this quadratic function, I have created a one-to-one function, and therefore it would have an inverse. So in order for us to talk about our trig functions, and let me show you this here, remember that our trig graphs are periodic in nature. They squiggle up and down like this. This is my sine function, and you can see just from the graph I have here that this is not a one-to-one function because it obviously doesn't pass the horizontal line test. But what if, instead of looking at the entire or a large picture of my function, what if I only want to look at a portion of this function between, let's say, negative and positive pi over 2? If I only look at this small piece of this sine function, you can see that it is one-to-one because I'm not looking any further to the right of this the right-hand bound, and I'm not looking any further on the left of this left-hand bound. So I just forced this sine function to be restricted it so that I could then say that it does have an inverse. Now, here's a summary of what inverse functions tell us, but the main thing that we're going to probably focus on here is the fact that if a function has an inverse, then the domain of the function is the range of the inverse, and the range of the function is the domain of the inverse. So they are flipped. And that's because if you were to look over here, when I'm thinking about inverse functions, all I have to do is switch, I believe it says it right here, or down here, all I have to do is switch their x and y values since they're related in this particular fashion, and I can then come up with its inverse function. So the domain switches with the range for the function, and the inverse domain switches with the range of the original functions, and you can see that's how we come up with both of their domains and ranges. Now, here I have a table of the inverse functions, And you can see it has all 6 of the trig functions that we've been dealing with. It gives the domain of each of the functions and their subsequent range. Now this is listed as the interval, but that is the range of the function that I'm going to be dealing with. And then if this is the range or the interval of my inverse function, then these are the quadrants that that inverse function lies in. And I'll explain that again in just a second. But let's just focus on our inverse sine function. The domain, or the allowable input values, the possible x values that I can have for a sine, for inverse sine, I'm only allowed to have numbers between negative and positive 1 for x. So if I input a number for x, or if I'm trying to find out the inverse sine of a number, that number I'm trying to find the inverse sine of has to fall between negative and positive 1. If you think back again to the graph of just sine, remember our sine and cosine functions bounce back and forth between positive and negative 1. So for a sine function, this is the range. For the inverse sine function, this is now the domain. See how they're switched? Okay. Moving on, we see that this is the possible input values for sine, and the output values, okay, the range, the area, the answer to the inverse sine of a function has to fall somewhere between negative pi over 2 and positive pi over 2. Now let me draw you a picture of what that's really stating. So if I'm looking for the inverse sine of a function, then the answers for the inverse sine function are going to lie somewhere here between positive pi over 2, right? This is positive pi over 2. And then this down here, although it could be 3 pi over 2 if we move in the positive direction, instead for the inverse sine we call it negative pi over 2. Now, how do I get to negative pi over 2? Let's back up for just a second and investigate this a little further. So when I find the answer, or in other words, the answer of my inverse sine function is going to lie here somewhere in between 0 and pi over 2, and then so that would be this angle theta, or it has to lie down here between 0 and negative pi over 2. So we have to move in the negative direction. My angle theta has to go negative in order for it to land down here in the 4th quadrant. So your possible answers, your possible solutions for the inverse sine function have to live here in quadrants 1 and 4. And that's similar for, or you have to take that into account when you deal with the rest of these trig functions as well. So when we talk about, say, the inverse cosine function, inverse cosine functions, possible answers are going to have to lie between 0 and pi, or somewhere up here in these 2 quadrants. And I leave it to you to investigate the rest of these, the remaining 4. To kind of really get an understanding. I highly encourage you to kind of get a visualization of where these take place, and drawing a picture of it is going to help out a lot. Now the last thing we're going to look at together is, let's take a look at this idea right here. We want to, let's say we want to consider the inverse cosine function. Now we define an inverse function as cosine inverse, or raised to the negative 1x. You may also see an inverse function written as arc cosine. Okay, so anytime you see arc tangent, arc sine, arc cosine, we're talking about the inverse sine, but I wanted to point that out to you. So if we're looking at the domain of cosine, or of inverse cosine, the domain of inverse cosine is going to be from negative to positive 1. And the possible range, or the possible outputs for cosine are again between 0 and pi. Between 0 and pi, which we drew a picture over here representing that. So this is 0, this is pi, and this right here is my inverse cosine function. So let's skip down here to this last question. It says, if the arc cosine or inverse cosine of negative 1/2 is equal to 2 pi over 3. Why then, when I take the inverse cosine of negative 1/2, is that not equal to negative 4 pi over 3? Well, let's first decide on this first question right here. This is the true part. It says the inverse cosine of negative 1/2 is going to be at 2 pi over 3. Where is 2 pi over 3 in my on this graph? Well, 2 pi over 3 is over here in the second quadrant. So if I were to draw this angle theta, this is 2 pi over 3. And because angle theta stayed within this allowable range, or within this blue zone, let's call it, then that is an acceptable answer. But let's talk about negative 4 pi over 3. Negative 4 pi over 3, if I were to move negative, remember I have to move in the clockwise rotation, and so moving over here, that's 3. This right here is negative 4 pi over 3. Notice, although I'm ending up at the same position in quadrant 2, in other words, 2 pi over 3 and negative 4 pi over 3 are coterminal with each other, I left the zone. That's what I call it. I came out of quadrants 1 and 2, right? I never went through them. Instead, I came out of the zone and entered in kind of the back door here, and that's not allowed. In order for my inverse functions, in order to have solutions to my inverse functions, I must stay entirely within their allowable range, or when I draw a picture like this, must be within the blue zone area. Okay, so here's an understanding. Hopefully you have an understanding of our inverse trig functions.